Hello everyone, this is the solution to the laboratory exam 4. Now here we have a state space problem to solve, and basically we have a function called full assignment. The arguments are PCS, the characteristic polynomial, PDS, the desired polynomial, and we return basically the state matrix, the input matrix A and B, KL, the state feedback controller, and the Limburger observer, and then also the controller, which consists of basically the controller and the observer. Now, we have a specific system where the output matrix is 1, 0, 0, 0. And yeah, we have a state space model of GS. So this one here is the model of this. And then, as we talked about the PCS and PDS inputs, we will use only the symbolic toolbox, and the input A and B should be calculated. We should design a controller, design an observer, and return the corresponding controller FSS. And whilst we have PDS, which is an input, which is meant to be for the controller design, we will have an internal PDS to use or to design this observer here that is equal to s plus 10 to the power of n. Well, initially this problem was designed for the nth order, a general solution, so I'm going to give you the general solution, which will not be restricted to the fourth order, but since it's a general solution, you can work out what n equals 4 would look like. And yeah, the controller here is basically the transfer function that takes the input y, which is the output of the system, and returns the control signal. Now, of course, this seems a bit odd because it is not really the strategy of a controller that we are used to, but since we are using state space and since we're using state feedback and Limburger observer, this will make sense when we try to solve it. Now, you are only responsible for n equals 4. If A and B is correct, K is correct, L is correct, etc. Now we also have an example code here, so I'm going to take this code, hopefully, like this, and I have an additional script here. So first of all, I'm going to call this like this, and we will be working with A and B first. If you want to solve the such problems, and if your output, the protocol here, is already defined, what you can do is you can do the following. If you don't work on KL FSS, and if you're just calculating A and B, in the function itself, you have to define them and set them equal to 0. That's one way of solving that problem, because once I'm going to call this function full assignment, I'm going to look for these outputs. And if you didn't define them in your function, then it'll crash, basically. So, and I also have this function here. What I mean by that is, initially, when you don't do anything, what you can go ahead and do is you can just equate them to 0, like this. So let me copy this part. And once you solve one of them, you'll just basically set that equal to what it should be. So yeah, and since I'm going to use the symbolic function, so let me just go up here, I'm going to define S. We were using PCS and PDS throughout the semester, so we basically expect that it will be a polynomial of the term S. So yeah. Now let's start by taking the coefficients here of PCS, like this. Let's call it Qf. Now, I'm going to show you the general solution here. Therefore, I'm going to assume that PCS is not always starting with a coefficient of 1 with the highest order term. So this could be 2 times s to the power 4, etc., etc. By the way, I am going to use the following strategy. In the laboratory sessions, I've talked about the fact that if I'm going to transition from a transfer function into a state space model, what I'll do is I'll just define a transfer function between the states and the input, because the A and B matrices are really about the characteristic polynomial of the system. Therefore, it is already given in 1 divided by PCS here. So it is all about A and B. and we have an output matrix already defined. So now, therefore, if we have 1 divided by PCS, you will see that it will be equal to 1 divided by this. And if I cross multiply the terms, I'll get basically this times x equals u. And yeah, if I work my way out, I'll see that x to the 4th derivative and then plus 2 times x to the 3rd derivative plus 4 times x double derivative plus 5 times x derivative plus x equals u. Now, if you define x1 equals x and take all the corresponding derivatives, which will be this, therefore it is this, and we will have x3, therefore it will be the next derivative, it will be double derivative, and then x4, the third, and then basically x4 derivative is already what we look for. We don't really have to define it as a new one because we have this term here. So you can see that each new variable will be the derivative of the previous one. Therefore, we have this structure here that is basically 0, comma, and then 1, comma, 0, comma, 0. And then we will have 0, 1, and then 0, 1. These are the previous 3 definitions here. So x2 is basically we have x1, x2, x3. It goes on like that. And we will have the derivatives. So therefore, it will just push this 1 on the diagonal here. And we will hit this boundary here. So basically the upper structure will look like this. Why? Because we have x2 derivative equals x3. x1 derivative equals x2. So x1 derivative, x2. x2 derivative, x3. And so on and so forth. But the last one, the last row in the A matrix, will be all about the actual differential equation that we look at. Because the 3 rows here are really all about the helper definitions, sort of speak. So therefore, you will plug in here x4 derivative, and you can see that this will be basically x4, then this will be x3, x2, and x1. And you already see the problem here. The highest order coefficient here will be used in order to normalize the coefficients here. So therefore I have to basically divide into this coefficient. So I have to divide into 2. So I'm going to get rid of that before I even start by normalizing my whole coefficient vector. If I do this, I basically have coef divided by coef1, so I got rid of this 2 because I divided into 2. So that's one thing. And the other thing is that basically x1 is the first term here that we are interested in. And I'm plugging in 1, and then 5, and then 4, and then 2. And you can see that it pops immediately up here, but the order is reversed. So what I can do is I can take basically coef starting from 2 up to the end, but I need to flip it. Again, I'm just giving the general solution. Therefore, this would be the last row. And before that row, I already know that I have a specific structure here. So A equals. Now, first of all, I need to know what the order is, and I can take the length of the coefficients vector, take -1 because I will have the constant term, and then so basically I will have n+1 coefficients if I'm talking about an nth order polynomial. Therefore, I'm subtracting 1 in order to recover what the order is. Now I have n, and I know that in this example I can see that If it's a square matrix, it will be n by n, but I know that there will be zeros in this column here specifically, so there will be n minus 1 zeros in this column, and then I will have n minus 1 by basically n minus 1 identity vector. So what I can do is I can just go ahead and code this. I know that I will have zeros, n minus 1 of them for this row, and then this will be followed by an identity matrix, n minus 1 by n minus 1. Then I'll have this flip here, but there will be a minus sign, and the reason for that is simple. You will just take these, put it here, so all the coefficients will have minuses. So I'm going to flip the vector, all the coefficients, but I'm not taking the highest order term because that's already on the left hand side. Therefore I'll start with coefficient 2, because coef 1 is the highest order term and it should stay on the left hand side because it is x4 derivative equals all the other stuff. So therefore it starts with 2 up to the end, flip it, and also flip the sign here. Once I have done that, I guess we would be good to go. If you're in another programming language, you might want to add n plus 1 here instead of n, because yeah, we have n plus 1 terms. So let's see if this is really working here, and let me comment this whole thing here out. So if I run 1, and hopefully MATLAB works, well, we need to define sims s in here, that's for sure. Run it again. There we go. Now you can see that I use zeros n minus 1 by 1, which is this column vector here. This is therefore a 3 by 3 identity matrix, and then I flipped the last row and flipped also the sign, and I also divided by 2. Since I'm using coefs here, it is a symbolic expression, therefore you can see that it is divided by 2, etc. So these are symbolic expressions. In order to prevent that, what you might do is you might just define a to its double, equal to its double. If I do that, I immediately get rid of these divide by 2s. So that's good so far, but yeah, if I'm looking at the structure, I already know that I have this as the differential equation. Therefore, this will be basically plus 0u, plus 0u, plus 0u, but here we have u. But since I divide it into this high order term here, it will still have 1 divided by 2 here. So it will not be directly u, but if I divide it into 2, you'll get this. So minus that, minus 2, minus 2.5, plus 2, or minus, I guess, then plus 0.5u. So don't forget to divide by the highest term for your B matrix. I already know the structure here that everything will be 0, but the last one will be 1. But I still have to use that dividing by the highest order term. So therefore, it might be a good idea to define something like this here, because I'm losing this information. And then instead of doing this, I might just also completely skip this out and say that, you know what, you will use flip that divided by an, and it will be equal to your A matrix. So let me just put it like this. Once I'm done with that, I can look for the structure. It will be dot dot dot, and then this would be 1. Again, I can use this here because it's already a column vector and its size is n minus 1, and the last term will be equal to 1, but I will divide into an. And let's also convert this into a double. Let's see. yeah, we have a missing parenthesis. Now let's see. Of course, I have to get rid of these two here. There we go. Now, if you have this, and if you're not sure if it's wrong or if it's working, what you can do is you can just look for SI, at least in order to control if A is correct. SI, since we are dealing with a fourth order system, SI minus I, this determinant here, should show you if you're still on the right track or not. Now, we have this 2 term here. So let me just basically check if it's correct. So S4, 2S, 3, 4S squared, 5S plus 1. If we have the highest order term here, we should be dividing into AN. We're dividing here by AN. And that should be good to go. Now, this is the A matrix and B matrix. So, of course, if you have a fourth order system, you can just skip this N here and code it, hard code it. But yeah, in order to show you the general solution, this is basically it. Now, of course, using this same structure here, what we can do is we can define C, because it was already given to us that C has a special structure here. And it is basically 1, comma, and then 1, comma, n minus 1. This should be the C matrix that we might need. Do we have that here? There we go. So we have the first item equal to 1 and all the rest is equal to 0. So that's good. Now, this is basically the solution for A and B. And let's go ahead and try to solve or try to design the controller itself. So we are given a PDS, and the first thing that we need to do here is to convert this into PDA, sort of. So we are substituting A into S in PDS, because this is one term of the Ackermann formula that we are going to use. So therefore this is necessary. But if you recall, we have a function called subs here. And if we use PDS S equals A, it will substitute A into S. But if you use this code in line 16, you will probably fail, because MATLAB has a strange thing that if you have A, you can add 1 to A, but it is not really what we expect here, because a scalar can be added to a matrix because there's such a thing called element by element. So this scalar will be operated on each element here, and all the entries of a matrix will be increased by that scalar or decreased. But we don't look for that. And if you use subs, this will happen no matter what. So in order to prevent that, we have to work around, because it's not really a thing that we would do, but we need to use a workaround. Here we can see a to the power of 4, 2 times a to the power of 3. Everything makes sense, but once it is done with this whole thing here, it will end up being a matrix, and then this would be a scalar. Adding a matrix to a scalar is different than adding a identity matrix to this whole structure here. So a quick workaround would be to subtract the last term, substitute into that, and then add this times the identity matrix. That could be one way of doing things, but I would rather skip that and just look for the coefficients of these terms and then do the operations. And yeah, that would be basically it. So let's do that. Let's do it the long way. Now, the calculation of PDA for K. So that's basically it. Now, let me just take this term, code here, replace that with PDS, because now I'm interested in a different polynomial. Now I will have the coefficients. Let's create a PDA variable here, and I'll use the for loop, starting from 1 to, I'd say, length coef length coef minus 1. And yeah, so I'll do this because I will be operating on this part here. If I would use length coef here, it would be up to this point. But I'll skip the last one because that will be multiplied with the identity matrix, but everything else is in terms of A. So I'm going to stop at the constant term, basically. So we should increase PDA. PDA equals PDA plus. Now this is a bit tricky, but we need to look for the coefficient, the ith coefficient here. And since we will start from the left, it will be the highest order term. We will multiply that with the power of A. So the power of A. And it will be basically the nth order, but I want to decrease this with increasing I. And if it's exactly equal to n minus n would give me 0, but that's not really it. So it should be n minus I plus 1 here. And I would say this is basically it. And once we're done with that, we will increase again PDA by coef, and the last entry here, so coef end times identity n. Again, I'm still coding with the nth order general solution, so therefore I'm using n, you might use this. But since this is basically not really necessary, what I can do is I can just begin with the initial value and add to it, and I can skip this last piece of code here. Another thing that is necessary in order to design a state feedback controller is basically the controllability matrix. Now we will have a similar code here, so let me just copy this. Here we'll have phi c, and let's start with basically b, because it always starts with b. And we will go up to n minus 1 here. Again, if you look up the formula, you'll see why. But this time, instead of increasing stuff, we will just increase the size. And we will add a to the power of I times b. Why? Because the formula goes like this: a times b, and then a squared times b, and you stop at a cubed times b, because there are 3 terms here and the initial term was b, so you have already 4 terms. And since you're working with n equals 4, you should stop there. And you can see that n is 4, but you should stop at 3. Therefore, the third power, each time I increases, you'll have the next power here, and you multiply it with b, and you're increasing or increasing the size of the vector or concatenating the vector with a new term. So that should be basically it. But since I'm still at it, what I can do is, for the observer part, before I even go on, for the observer part, I need a similar thing here, which would be called phi o, but that would start with c, and then phi o would be extended with c times a to the power of I, and of course the direction of extension is a bit different. They should be on top of each other. These should be side by side. So that is basically it. At this point, I have phi c, I have PDA. All that left would be to, again, we need a certain structure here, but then the inverse of phi c, and then times PDA. Let me get rid of c because that's not necessary. So this structure is already familiar because we already had that. So this would be a zeros vector, one row, n minus 1 columns, and the last term would be equal to 1. And then we take the inverse and then PDA, etc. So I'm not really sure if this is a symbolic expression anymore. So to be safe, I can just do this conversion and we should be good to go with k. So I want to see what k is now. K is this. In order to see if it's really correct or not, I can see I have the eigenvalues -1, -2, -3, and -4, which was initially this PDS here. Here, you can see that one of the poles is -1, the other one -2, -3, and -4. And you can see these are the eigenvalues. The poles of a transfer function correspond to the eigenvalues of A. So therefore, we should be good to go. And since this is closed loop, I have u equals -kx. And since it was ax plus bu, we will have a minus bk times x in the closed loop. Therefore, the state matrix of the closed loop is a minus bk. And therefore, we have a working controller here. So now, if you have done this, designing the observer is not really that big of a deal. But let's try to do this. We have a PDS, and I'm going to generate again the PDS here. So we need basically again a coefficient vector and PDA, but let's define PDS as it was given to us, s plus 10 to the power of n. And that's basically it, because we will assign all the poles of the observer to -10 instead of -1, -2, -3, and -4, as it was the case for the controller. So here I have PDS, another PDS that is necessary for the observer. This PDS was belonging to the controller. So I take the coefficients. I again do the same stuff here. You might take the A transpose route here. If you're not really familiar with the whole thing, what you can do is you can just plug in A transpose and then you have the same structure here. But what you also might do is to just use the Ackermann formula for the observer, which is not really that difficult. So let's do that. We have phi o, we will take the inverse of that. We have PDA, and therefore we can just go ahead and look for the observer here. So L, and then L, and then L. So since it is about the transpose, we will just reverse the order. So instead of doing this, we'll use PDA times inverse of phi o times, now it will be a n minus 1 by 1, and we will add a 1 there. It's basically the same formula, but if you look for the transpose, where is it? Here it is. If you take the transpose of this, the order will reverse. So PDA will become first, inverse phi o is still there, and then you will have the transpose of this. So it's really easy. So up to this point, we have basically solved. So A minus L times C should give us that, but we didn't really define C, but we had C, so let's maybe copy that. So I have defined it internally, but not out here. Well, let's do it like this. So n equals 4, therefore this is basically it. you can see that we have basically minus 10, minus 10, minus 10, and minus 10. And we don't really have to care about the numerical sensitivity in this case because, yeah, 4 poles on top of each other, it is pretty much expected to have this numerical sensitivity in this case. This is practically 0 and this is practically minus 10, so no problem there. Now we have basically solved for A, B, K, and L. So let me recap before I go on with FSS. So we have PCS and PDS. This will give us the A and B matrices, as it is the case here. By the way, I used basically the controllable canonical form, but you don't really have to memorize that, because if you follow on along the instructions, if you just define it between x and you skip all the numerator part here given for your transfer function, you will end up in the controllable canonical form. So therefore, it's pretty much easy to convert a transfer function into state space. All that I've done here is to define the 0 row that was necessary. Basically, we have A here, I can show it here. We have 3 consecutive zeros on top of each other, and then there's an identity matrix, because each time I define a new variable, it will be equal to the previous derivative. So therefore, if it's on the second column and first row, it's basically x2 equals x1 derivative. If it's here, it is x2 equals x2 derivative is equal to x3, and so on and so forth. So therefore, this structure will never change if we are using this canonical form here, and we have the 0. So we dealt with this. And the last row here indicates basically the differential equation, the normalized coefficients. The highest order term is somewhere here, but we don't really use that. We flip the signs and the order of the coefficient vector, and that was basically it for the A matrix. For B, we again had zeros, and the last term was u, because this is our differential equation. Our input goes into this equation, not the others. We've defined them, so therefore this should be u. But because of the normalization, I have to divide by an of all the terms here. We were given what C was, so that's not really relevant. Then it was really important to take the coefficients of PDS, but instead of using subs on PDS, to work around and add PDA the terms that were necessary. So take the coefficient, take the S power, but instead of S, plug in A and use that. Again, I repeat, you can just substitute into PDS minus its constant term and then add that constant term like this. It's also possible. And the problem here was that we had PDS here, and this term was messing up the whole thing here. So yeah, be careful of that. Then we just worked our way out of generating the controllability and observability matrices. We're just adding the structure. So this is basic MATLAB code. And then we just applied the Ackermann formula to both here. We were given that the PDS of the observer, so the desired polynomial for the observer, was already fixed to s plus 10 to the power of n, so we used that. Now, we have a controller, we have A and B matrices. By the way, we have the whole system here because there's D0 and C is this. Now, what about the transfer function that was requested from us down here? So what about that? Now, for this, you might need a little pen and paper to work out what it really is. But once you get the hang of it, it will be really interesting. Let's see if our K matrices, by the way, are the same. 23, 45, it seems like to be the same, and L, yeah. Now, this whole thing here might scare you off, but it's not really that problematic. So we have this equation here, u equals minus kx. So that's one thing. And we also have this dot, so dx equals ax plus bu plus L times y minus L times y hat or bar, whatever you call it. So let me show you. This set of equations are basically important in order to work out what FSS looks like. Because ideally, we would use u equals minus kx. But here's a hint that we are not really using the system states because for some reason we don't really have them, we don't measure them. So we are using the states of the observer, and an observer is responsible for generating us this information. We're taking basically the output of the observer, connected to our controller, and our controller will provide us the control signal. And the observer here uses basically u and y, because all the other stuff with hat is an internal signal of the system, of the observer itself. So the external inputs will be u and y. But since we plug in u equals minus kx hat, u is not really an external signal. So therefore the only external signal of the observer becomes y. So our whole system of control has an input of y. If you give me y, the observer can give you basically x, and your controller can take that x and convert it into the control signal. And you can see that I need the input y and output u as a transfer function. So it seems like I need to use this and this equation in order to look for this transfer function here. So it was here. So we have this equation here, ax plus bu plus ly, and this is not x, this is x hat. So if I plug this into here, it will become minus k x hat b times basically. So this is basically the end result here, but we have a common factor, so it will look like this. So this is a minus bk x hat plus ly minus ly hat. But I know that this is basically L times C x hat. Again, we have this here. So let me move it. So it will become LC. So B times K, L times C. Now, we're basically almost done. This is x hat derivative equals something times x hat plus L times y. Whereas this is basically the output equation, because u is the output in this case, because we're talking about the controller, and minus k times x. So let me state the following. So AL is basically this matrix here. BL, this is the input. Y is the input of the controller, or the observer, which is included into the controller. So therefore BL is equal to L. And CL is basically this. Y equals C times X. So U and Y, all the definitions might confuse you, therefore you might need a pen and paper. But if you get the hang of it, it will become obvious, hopefully. So this is equals minus K, and DL is equal to 0 because there's no direct connection. If there were something like this, like let's say 2 times Y, then D would be equal to 2. But that's not really the case, so I can skip that. So therefore I've worked out what the matrices are. The only thing that is left here is to convert it into a transfer function. Now, since it is FSS, it's defined in the symbolic toolbox, what you need to do is you need to follow the C times S times identity minus A times B plus D, but D is 0. So that would be basically the definition that we look for. Of course, these should be CL, A, L, and BL. And if you define these, DL is equal to 0, you should be good to go. Now let's see if we are on the right track. And let's see, we have AL and then minus K. Of course, in this case, I should maybe still generalize it like N S times I minus A, which is that, okay, times BL, which is L. Of course, I forgot to take the inverse here. C times SI minus A, the inverse, times B. So there we go, because it should be a, yeah, there we go. Now this again seems a little bit troubling. So what we can do is we have a simplify fraction command. So we can use that on FSS. And you'll see we have a better output. So is it the output that we were, or did we have FSS? So we can see it kind of is. So 50277. But you might ask yourself, how did we generate this how did we generate the closed loop here? So this closed loop transfer function here. So in order to do that, we have to basically, well, we can use, one way is to define GSS as 1 divided by PCS. So the open loop, we have the controller, so why not look for the feedback here? So we need to look for the feedback, but here we will have this minus sign, which might confuse you, and it really depends on U minus KX. So since this is, since we have minus included in K, we need to take another minus in order to end up in the actual feedback, because most of the time if we use the feedback command, so let's have FSS and GSS and then this branch here. So if this is the case, we will have basically a minus sign here for this branch here. But in this case, U is equal to KX, so we don't have that minus sign, so the closed loop would be, so this seems like a positive feedback, so we have to include the minus sign here. So 1 minus FSS times GSS. Of course, once we have defined that, what we can do is we can just take the numerator and denominator. We could have also converted everything into TF before we start to look for the feedback and then acquire the closed loop, but it doesn't really matter. And well, the TS in TF would then look like this, the double, and then if you have TF to sim, sim to TF, you can just use that, or I'm going to just show you what it looks like. So DS, and that should be it. So let me get rid of this. Yeah, seems to be all right. So we have this TS, and if I look for ZBK, I get basically the output that I wanted to. Now, an interesting note is the following. We have FSS, which looks like this. And you can see that it is not really a static feedback controller anymore. It is a fourth order controller. In our control system design lectures, we didn't really design a fourth order controller if it's a model matching controller, etc., we might have done it. But other than that, we didn't really design fourth order controllers. But it seems like if you use an observer, since the system is a fourth order system, the observer is a fourth order copy of the system, and then you have a static feedback. So you have a bunch of p-type controllers for each x. You can think of it like that. So therefore, the controller itself has no basically order to itself. It doesn't use any integrate or whatever. But the observer has a fourth order dynamic because it's the copy of the system. And connecting them together gives us this fourth order controller. So if you use an observer and a state feedback controller together, you'll get a high order controller. And the controller itself has basically the system model in itself. So in that sense, it makes sense. And in the closed loop, we have 4 poles that belong to the observer. We have the actual system closed loop poles that we were looking for, and also some zeros that are obviously belonging to the controller itself. So it is interesting because it needs to have all the states in order to have a state feedback. But if it's not available, you just generate it. So the controller has some sort of the system information embedded into it, and it is a higher order controller than expected, because most of the time we would attack this problem by designing a PID controller which would have just S here and then 2 zeros here. So there are far more zeros and poles in the controller itself. But that's not really the topic of today. We have basically achieved what we were looking for. Now, this lab exam is a more technical one. Hope that it helped you out in diving deep into the state space model and to experiment with that. See you soon.